Welcome back. Last episode, we discovered the Taylor series. Today, we tackle the question we left open. Where does a Taylor series, or more generally, an infinite polynomial of the form the sum of c sub n times the quantity x minus a to the n actually converge? The general object is called a power series. It's an infinite polynomial centered at a point A with coefficients c sub n. The Taylor series is the special case where c sub n equals the nth derivative of f at a over n factorial, but a power series doesn't have to come from a function. You can just write down coefficients and ask, for which x does this sum converge? The answer is beautifully clean. Every power series has a magic number r between 0 and infinity inclusive, called the radius of convergence. For the absolute value of x minus a less than r, the series converges absolutely. For the absolute value of x minus a greater than r, it diverges. On the boundary, where the absolute value of x minus a equals r, the behavior depends. Sometimes converges, sometimes diverges, has to be checked. To find r, the ratio test gives a one-line formula. R equals the limit of the absolute value of c sub n over c sub n plus 1. Inside the radius, power series behave like polynomials, differentiate and integrate term by term, and the new series has the same r. That's the whole episode. Let's go. Start with the definition. A power series centered at A is a formal expression, the sum of c sub n times the quantity x minus a to the n with constants c sub n. The n equals 0 term is just c sub 0. The n equals 1 term is c sub 1 times the quantity x minus a, and so on. 3 quick examples. The geometric series, the sum of x to the n, equals 1 plus x squared, and so on, is a power series with c sub n equals 1, centered at a equals 0. The exponential's Maclaurin series, the sum of x to the n over n factorial, has c sub n equals 1 over n factorial, centered at 0. You can also pick a different center. The sum of the quantity x minus 3 to the n over 2 to the n is a power series centered at a equals 3, with coefficients 1 over 2 to the n. And here is a power series that will turn out to be very strange, the sum of n factorial times x to the n, where the coefficients are the factorials. Spoiler, it converges only at x equals 0. Question. Fix a power series. For which values of x does it converge? At x equals a, every term except the n equals 0 term is 0, so the sum trivially equals c sub 0, so every power series converges at its center. The real question is, does it converge anywhere else? And if so, where? The remarkable answer. The set of x where the series converges is always an interval centered at a, with some radius r between 0 and infinity. Let's prove it. Why is the convergence set always an interval? One beautiful lemma. Suppose the series converges at some point x not equal to a. Claim it converges absolutely for every x closer to a than x naught is. Proof sketch. If the sum of c sub n times the quantity x naught minus a to the n converges, the nth term test forces c sub n times the quantity x naught minus a to the n to approach 0, hence bounded. The absolute value of c sub n times the quantity x naught minus a to the n is less than or equal to m. Now pick x with the absolute value of x minus a less than the absolute value of x naught minus a. Write the absolute value of c sub n times the quantity x minus a to the n as the absolute value of c sub n times the quantity x naught minus a to the n times the absolute value of the quantity x minus a over x naught minus a to the n. First factor bounded by m. Second r to the n with r less than 1. So the absolute value of c sub n times the quantity x minus a to the n is less than or equal to m times r to the n. That's m times a convergent geometric series. Comparison test, the sum of the absolute value of c sub n times the quantity x minus a to the n converges. The power series converges absolutely at x. That's the heart of the theorem. Convergence at any single point x naught forces convergence on the whole open ball of radius, the absolute value of x naught minus a around a. The convergence set is star-shaped around a, which in one dimension means an interval. Take the supremum of such radii, call it r, and you have the radius of convergence. Stating it properly, for every power series, the sum of c sub n times the quantity x minus a to the n, there's a unique r in the closed interval from 0 to infinity, the radius of convergence, with 3 properties. If the absolute value of x minus a is less than r, the series converges absolutely. If the absolute value of x minus a is greater than r, it diverges. If the absolute value of x minus a equals r, behavior depends on the series, check each endpoint separately. 3 regimes. R equals 0 converges only at the center. The pathological case. R equals infinity converges for every real x, e to the x, sine x, cosine x, live here. And r finite and positive, a genuine interval with 2 boundary points. The interval of convergence is the set of x where the series converges. Always one of 4 shapes, The open interval, one of two half-open intervals, or the closed interval. Which one depends on the endpoints a plus or minus r? The interior is determined by r. The endpoints take separate analysis. One of the cleanest theorems in analysis. Power series have a sharp cutoff with predictable behavior inside and out. How do you actually compute r in practice? Apply the ratio test from episode 13. Set a sub n equals c sub n times the quantity x minus a to the n, the general term of the power series. The ratio test wants the absolute value of a sub n plus 1 over a sub n, which factors as the absolute value of c sub n plus 1 over c sub n times the absolute value of x minus a. The ratio test says the series converges absolutely if the limit of this ratio is strictly less than 1, and diverges if it's strictly greater than 1. So convergence happens when the absolute value of x minus a times the limit of the absolute value of c sub n plus 1 over c sub n is less than 1, which means the absolute value of x minus a is less than 1 divided by that limit. Comparing to the definition, the absolute value of x minus a less than r, we read off r equals 1 over the limit of the absolute value of c sub n plus 1 over c sub n, or flipping numerator and denominator, r equals the limit of the absolute value of c sub n over c sub n plus 1. That's the formula. Memorize it. Subtle point, this formula requires that the limit of the absolute value of c sub n over c sub n plus 1 actually exists. For most power series you'll meet, it does. But there's a more general formula due to Cauchy and Hadamard, using the root test, 1 over r equals the limit superior of the absolute value of c sub n. The limit superior always exists, so this formula always works. For us, the ratio test version will be enough. We'll use the root test in one example near the end. Time to compute. First worked example. Find the radius of convergence of the sum of x to the n over n factorial, which we know is the Maclaurin series of e to the x. Read off the coefficients, c sub n equals 1 over n factorial. Compute the ratio, the absolute value of c sub n over c sub n plus 1. That's 1 over n factorial, divided by 1 over the quantity n plus 1 factorial, which flips into the quantity n plus 1 factorial over n factorial, which telescopes to n plus 1, so the ratio is just n plus 1, and its limit as n approaches infinity is infinity. Therefore, r equals infinity. The series converges absolutely for every real x. Confirms what we said last episode. E to the x converges everywhere, now derived from the radius formula directly. The factorial in the denominator makes the coefficients shrink so fast that no value of x, no matter how large, can outrun them. Same story for sine x equals the sum of negative 1 to the n times x to the 2n plus 1 over the quantity 2n plus 1 factorial, and cosine x equals the sum of negative 1 to the n times x to the 2n over the quantity 2n factorial. The factorial denominators force r equals infinity. These three series live on the entire real line. Second example. The series, the sum of x to the n over n, starting from n equals 1 to avoid dividing by 0. Coefficients c sub n equals 1 over n. Ratio 1 over n divided by 1 over the quantity n plus 1 is the quantity n plus 1 over n, which tends to 1. So r equals 1. Series converges absolutely for the absolute value of x less than 1, diverges for the absolute value of x greater than 1. So far so good. Now the interesting part, the endpoints. At x equals 1, the series becomes the sum of 1 over n, the harmonic series. We know from episode 12 that this diverges, so x equals 1 is not in the interval of convergence. At x equals minus 1, the series becomes the sum of negative 1 to the n over n, the alternating harmonic series. By the alternating series test from last episode, this converges. So x equals minus 1 is in the interval of convergence. Putting it together, the intervals of convergence is from minus 1 to 1, closed on the left, open on the right. This is the prototypical example of why endpoints need separate analysis. Same r on both sides, but the endpoints disagree. One converges, one doesn't. The structure is asymmetric because the alternating signs at x equals minus 1 rescue the convergence that fails at x equals 1. Side note, this power series, slightly reindexed, is the Maclaurin series of minus the natural log of 1 minus x. So we just proved minus the natural log of 1 minus x has interval of convergence from minus 1 to 1, closed on the left, open on the right. Third example, the strange one. The series, the sum of n factorial, times x to the n, with coefficients c sub n equals n factorial. Ratio, n factorial divided by the quantity n plus 1 factorial, which is 1 over n plus 1, which tends to 0. So r equals 0. That is bad news. R equals 0 means the series converges only at the single point x equals 0. For literally any other value of x, the series diverges. Sanity check it. Fix any x not equal to 0. The nth term is n factorial times x to the n. For large n, the factorial n factorial grows faster than any fixed exponential, the absolute value of x to the n. That's a fundamental fact about factorials. So the terms n factorial times x to the n blow up in absolute value, failing even the nth term test for convergence. So this power series is essentially useless as a function. It's defined only at x equals 0, where it trivially equals 0, factorial times 0 to the 0, which is 1, using the convention 0 to the 0 equals 1 here. It is the most degenerate power series possible, but it illustrates an important point. Not every infinite polynomial corresponds to a function. Plenty of formal power series have r equals 0 and define nothing. The radius of convergence is a real constraint, not a formality. Fourth example, non-trivial center. Consider the sum of the quantity x minus 3 to the n over 2 to the n, centered at a equals 3 with coefficients c sub n equals 1 over 2 to the n. Ratio 1 over 2 to the n over 1 over 2 to the n plus 1 equals 2. So r equals 2, and the series converges for the absolute value of x minus 3 less than 2, that is, x between 1 and 5. Endpoints at distance 2 from center 3, x equals 5 and x equals 1. At x equals 5, each term is 2 to the n over 2 to the n, which is 1. The sum of 1 diverges. At x equals 1, each term is the quantity minus 2 to the n over 2 to the n, which is negative 1 to the n. The sum of negative 1 to the n diverges by oscillation. Neither endpoint included. Interval of convergence, the open interval from 1 to 5. Bonus, closed form. Substitute u equals the quantity x minus 3 over 2, and the series becomes the sum of u to the n, which is 1 over 1 minus u, valid for the absolute value of u less than 1. Substitute back 1 over the quantity 1 minus the quantity x minus 3 over 2, which is 2 over the quantity 5 minus x. That function has a pole at x equals 5, exactly the right endpoint. The series agrees with 2 over 5 minus x inside the interval from 1 to 5, but can't see past the singularity. Picture this: the geometry of the radius of convergence on the real line. In the middle, the center A. Stretching both sides, the interval of convergence, total width to r. Inside, shown in blue, the series converges absolutely. Outside, stretching to both infinities, it diverges. At the two endpoints, a plus or minus r, behavior is undetermined by the formula. Sometimes the endpoint is included, filled dot. Sometimes excluded, open circle. The two can behave independently. We saw it with the sum of x to the n over n. X equals minus 1 included, x equals 1 not. The asymmetry between interior and boundary is the whole story. Inside, automatic via comparison with a geometric series. Outside, automatic, nth term test fails. Boundary, delicate, full convergence toolkit from last episode. This figure is the answer to the opening question. Where does a power series live? On a ball around A of radius r, with the boundary needing separate work. Now, a beautiful structural theorem. Power series, inside their radius of convergence, behave exactly like polynomials. You can differentiate them term by term, you can integrate them term by term, and the resulting series have the same radius of convergence. Formal statement. If f of x equals the sum of c sub n times the quantity x minus a to the n converges for the absolute value of x minus a less than r, then inside that interval f is differentiable with f prime of x equals the sum of n times c sub n times the quantity x minus a to the n minus 1, that's the derivative of each term, and f is integrable with the integral from a to x of f of t, dt equals the sum of c sub n times the quantity x minus a to the n plus 1 over n plus 1, and the radius of convergence of both the differentiated series and the integrated series equals r. Why is this remarkable? Differentiation generally doesn't commute with infinite sums. A pointwise convergent series of differentiable functions need not have a differentiable sum, and even if it does, the derivatives don't have to add up correctly. Power series are an exception. Inside their radius, they're uniformly convergent on closed subintervals, which is strong enough for term-by-term calculus to work. Why is the radius preserved? Because multiplying coefficients by n or dividing by n plus 1 doesn't change the limit of the absolute value of c sub n over c sub n plus 1, the leading behavior of the ratio depends on the c sub n, and the polynomial factors in wash out in the limit. Time to use the theorem to do real work. Let's derive the Maclaurin series for the natural log of 1 plus x by integrating the geometric series. Start with the geometric series in the form 1 over 1 plus x equals the sum of the quantity minus x to the n equals 1 minus x plus x squared minus x cubed, and so on, valid for the absolute value of x less than 1, with radius of convergence r equals 1. Now integrate both sides from 0 to x. On the left, the integral from 0 to x of dt over 1 plus t. This is a standard integral. The antiderivative of 1 over 1 plus t is the natural log of 1 plus t. So the integral equals the natural log of 1 plus x minus the natural log of 1, which equals the natural log of 1 plus x. On the right, by the term-by-term integration theorem, since we're inside the radius of convergence, we can integrate the series term by term. Each term, the quantity minus t to the n, which is negative 1 to the n times t to the n, integrates to negative 1 to the n times x to the n plus 1 over n plus 1. Summing, the sum of negative 1 to the n times x to the n plus 1 over n plus 1. Reindex with n going to n minus 1, the sum from n equals 1 to infinity of negative 1 to the n plus 1 times x to the n over n, which equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on. The Maclaurin series of the natural log of 1 plus x. Same radius of convergence as the geometric series we started from, r equals 1. That's the theorem in action. Term-by-term integration preserves the radius. This is the slick derivation of the natural log series we used last episode. The term-by-term integration theorem turns the geometric series, which is trivial, into the natural log series, which is non-trivial. Time for a definition that wraps up the whole Taylor series story. A function f is called real analytic at the point a if there exists a positive radius r such that f of x equals its Taylor series for every x in the open interval from a minus r to a plus r. So real analytic means the Taylor series doesn't just exist, doesn't just converge, but actually equals the function on an open interval. Most familiar functions are real analytic on their domains. Polynomials are trivially real analytic everywhere. They equal their Taylor series exactly. The transcendentals, e to the x, sine x, cosine x, and their hyperbolic versions, hyperbolic sine x and hyperbolic cosine x, are real analytic everywhere on the real numbers with r equals infinity. Some functions are real analytic on a subset. The logarithm, the natural log of x, is real analytic on its domain, the interval from 0 to infinity. But the radius of convergence of its Taylor series at a for a greater than 0 depends on a. Specifically, r equals a, the distance to the singularity at x equals 0. Similarly, 1 over 1 minus x is real analytic everywhere except x equals 1, with r equal to the distance to that pole. The square root of x, arctangent x, arcsine x, all sine x, all real analytic on their natural domains. The slogan, almost every function you'll meet in calculus is real analytic on its domain. The Taylor series machine actually works for the functions you care about. That's the optimistic story. And now the famous counterexample. The example that shows real analytic is a strictly stronger condition than smooth. Define f of x to be e to the minus 1 over x squared when x is not 0 and f of 0 equals 0. Extension to 0 is fine because minus 1 over x squared approaches minus infinity, so e to the minus 1 over x squared approaches 0. Here is the shocker. This function, f, is infinitely differentiable everywhere, and at x equals 0 every single derivative equals 0. f of 0 equals 0. f prime of 0 equals 0. The nth derivative of f at 0 equals 0 for every n. The proof, near 0, derivatives are polynomials in 1 over x, times e to the minus 1 over x squared. The exponential factor decays faster than any polynomial in 1 over x grows. So every derivative at 0 exists and equals 0. Now write down the Maclaurin series of f. All coefficients are the nth derivative of f at 0 over n factorial, which is 0. The series is identically 0, converging to 0 everywhere. But f is not the 0 function. F of 1 equals e to the minus 1, about 0.368. So the Maclaurin series converges, with r equals infinity, but converges to the wrong function. The Taylor series knows nothing about f away from 0, so f is smooth but not real analytic at 0. Smoothness does not imply analyticity. Analytic is strictly stronger than C infinity. This counterexample seeds an entire field. Functions like e to the minus 1 over x squared are used to build bump functions, smooth functions exactly 0 outside a small region. Bump functions are the basic tool of differential geometry, distribution theory, and partial differential equations. You can't build them from analytic functions because an analytic function vanishing on a set with an accumulation point is identically 0. The non-analytic smooth functions are a feature, not a bug. A short historical note. The theory of power series and radius of convergence is largely the work of two giants of 19th century analysis. Augustin Louis Cauchy, in his 1821 textbook Cours d'Analyse, gave the first rigorous treatment of infinite series. He introduced the ratio test, the root test, and what we now call Cauchy's general convergence criterion. The radius of convergence theorem in essentially the form we've used today is due to him. Before Cauchy, mathematicians manipulated series formally without worrying about convergence. Cauchy demanded rigor, and the modern theory of series was born. Karl Weierstrass, working in the middle of the 19th century, built the theory of analytic functions on top of Cauchy's foundation. His definition is the one we gave today. An analytic function is one that locally equals its Taylor series. Weierstrass emphasized uniform convergence, gave the first fully rigorous proof of term-by-term differentiation of power series, and developed analytic continuation as the central tool of complex analysis. The cleanest, most general statement of the radius theorem is the Cauchy-Hadamard formula. 1 over r equals the limit superior of the nth root of the absolute value of c sub n, published by Jacques Hadamard in 1888. It requires no existence of the simple ratio, limit. The limit superior always exists. The pattern, 18th century mathematicians manipulated infinite series freely and productively. 19th century mathematicians laid the rigorous foundations underneath them. Today's tools all come from that 19th century rigor revolution. Recap. A power series is the sum of c sub n times the quantity x minus a to the n centered at a. The Taylor series is the special case c sub n equals the n the derivative of f at a over n factorial. Every n factorial, every power series has a radius of convergence, r in the closed interval from 0 to infinity. Inside, the series converges absolutely, outside, it diverges. On the boundary, it depends, and you have to test each endpoint by hand. Find r via the ratio test. R equals the limit of the absolute value of c sub n over c sub n plus 1. The more general Cauchy-Hadamard formula uses the root test. 1 over r equals the limit superior of the absolute value of c sub n. The interval of convergence is the open interval from a minus r to a plus r, plus possibly one or both endpoints, giving 4 possible shapes. Worked examples, the sum of x to the n over n factorial has r equals infinity. The sum of x to the n over n has r equals 1 with interval from minus 1 to 1, closed on the left, open on the right. The sum of n factorial times x to the n has r equals 0. Inside the radius, you can differentiate and integrate term by term, and the resulting series has the same r. This gave us the slick derivation of the natural log series from the geometric series. A function is real analytic at a if it equals its Taylor series on some open interval around a. Most calculus functions are. The famous counterexample is e to the minus 1 over x squared extended by 0 at the origin. Smooth, all derivatives vanish at 0, but the function itself is not 0. Smooth doesn't imply analytic. Power series complete the story of one variable calculus. Next series, we step out of one dimension. See you there. That's power series and the radius of convergence. Every power series has a sharp cutoff r. Inside, converges absolutely. Outside, diverges. On the boundary, depends. One formula, the ratio of coefficients, finds r. Inside, term-by-term differentiation and integration work and preserve r. Real analytic functions are the ones equal to their Taylor series. A to the minus 1 over x squared shows that smoothness is strictly weaker than analyticity. If this helped, like, subscribe, drop a comment. Tell me a power series you've encountered with a curious radius of convergence, or one whose endpoint behavior surprised you. Next series, we leave one variable behind, functions of several variables, the three-dimensional coordinate system, surfaces in space, partial derivatives, gradients, level sets, multivariable integration. The whole second half of calculus, starting with the basic geometry of 3D space. See you there. Power series complete the story of one variable calculus. We started with limits, derivatives, and integrals. We built infinite sums, learned which converge, and saw that smooth functions expand as Taylor series. Today's discovery, every power series the sum Cn of x minus a to the n has a sharp cutoff r, the radius of convergence, inside which it converges absolutely and outside which it diverges. The ratio test gives r in one line, r equals lim Cn n plus 1, and we computed it for e to the x. R equals in emph dice, the natural log of 1 plus x, r equals 1, and the sum n, x to the n, r equals 0. Inside the radius, power series behave like polynomials. You can differentiate and integrate them term by term, and the new series has the same r. That trick let us derive the natural log of 1 plus x by integrating the geometric series. We met the real analytic functions, those equal to their Taylor series on an open interval, and the pathological e minus 1 x squared, which is smooth at 0 but whose Maclaurin series is identically 0. Next series, we step out of one variable. Functions f of x, y live on surfaces in three-dimensional space. We'll build the 3D coordinate system, learn to visualize surfaces, and prepare the ground for partial derivatives, gradients, and multivariable integration. Subscribe and don't miss it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.